Should we go ahead? Inshallah today, يعني شباب, we are done with the first two chapters, which are يعني almost introduction, just a theoretical introduction to the internal combustion engines. Just to give you an idea about the application, I prefer to go with this sequence instead of starting with the combustion chemistry, gas mixing, and all of that. I want to make it a little bit interesting to just know about the internal combustion engine, some ideas about the vehicles and operation, and it is some general idea for the internal combustion engine. It is not more than introduction. Inshallah, today we'll be starting the part related to the chemistry or the combustion chemistry. Today we'll be starting with the gas mixing, mole fraction, mass fraction, how to calculate the molecular weight of a gas mixture, the gas constant, specific heat for a gas mixture, and how to calculate the other properties also for the gas mixture, like internal energy, enthalpy, the entropy. I think all of this actually you have heard about, and I think actually you know about it. But just I have to introduce it again here. So just a kind of refreshment, because we will need it actually in this chapter. Inshallah, this chapter, شباب, but before I proceed, don't feel panic. It's a simple combustion chemistry. So here, inshallah, we'll talk about the combustion equation and how to write down the combustion equation for any fuel, and calculate the air to fuel ratio, and calculate what's called the equivalence ratio. So inshallah, we'll consider the basic combustion. We consider complete combustion without any kind of kinetics, just actually the general formula for the combustion, the general combustion equation for assuming complete combustion. So it's very simple. Then we can calculate the air to fuel ratio and see actually the engine performance at the different air to fuel ratio, considering different fuels also. So inshallah, shabab, in this chapter, we'll start simply with the gas mixing. I'll be talking about Dalton and Dalton law for mixing of a gas mixture. Then we'll be talking about mass fraction and the volume fraction, and I think you know about that. Then actually, if we have a gas mixture, how to calculate the properties of this gas mixture, like the internal energy, enthalpy, how to calculate also the specific heat at constant temperature, specific heat at constant volume, if we have a gas mixture. Inshallah, we'll be talking also about the combustion process, how to write down the combustion equation, considering the air combustion case, considering actually different kind of fuel. If we have different fuel, how to write down the combustion equation, the general equation, as I said, without any kinetics, any intermediate reaction are not involved, just actually the general reaction. We will write down this equation, and we will learn, inshallah, from this equation how to calculate the air to fuel ratio, and then how to calculate what's called the equivalence ratio. Equivalence ratio, شباب, is the ratio between the fuel to air ratio actual divided by the fuel to air ratio theoretical. Theoretical, شباب, or stoichiometric, that means this is the fuel to air ratio, or we have the amount of air that is just enough to burn the fuel. We call it the theoretical. If we have more air, we call it excess air. If we have actually less air, in this case actually less than the theoretical, then in this case we don't have enough air for the combustion, so the combustion will be almost actually incomplete combustion. And that's why, shabab, we need to calculate the equivalence ratio. It will give us indication about the actual air to fuel ratio with respect to actually the theoretical air to fuel ratio. Do we have excess air, or do we have less air? Okay. So inshallah, we'll be learning how to calculate the equivalence ratio. Then we'll be considering the combustion of different fuel, how to write down the combustion equation for the different fuel. Okay, is that clear, shabab? So for the mechanical engineering student, we should not say student, actually are almost engineer, So inshallah, the course will not be in deep to the chemistry. Just it's something simple and something that you have to know about. Okay. Do you have any comment, ya shabab, before I can go ahead and start the class? Do you have any comment on this chapter?
No, everything, inshallah, will be okay.
Inshallah, it will be fine. The whole course will be fine. Inshallah, today, shabab, we'll be talking about the gas mixing. So I know you are, most of you especially actually the chemical engineering engineers. I think you know about actually the gas mixing and all what I'm talking about today. I think you know about. But let's say take it as a kind of refreshment. So if we have a gas mixture inside any container, so here we have actually a gas mixture, but this shabab is a gas. We don't have liquid. We are talking about gas mixing. As we say, the shabab, we are concerned with the liquid in the gaseous phase because, as I told you, liquid does not burn in the liquid phase. It has to be in the vapor phase. And that's why we are concerned here actually with the gas mixing. So let's consider we have a gas mixture inside a container consisting actually of different species. Let's say A, species B, C, and so on, whatever actually is the number of species here. So in order actually to calculate the properties, we have to know actually first of all about the partial pressure or the total, how to calculate actually the total pressure of this gas mixture. Starting with the Dalton law, Dalton said actually that the partial pressure actually or the total pressure is equal to the summation actually of the partial pressure for all components. Partial pressure of A, component A, plus partial pressure of B, plus partial pressure of C, and so on actually, whatever actually is the number of components in this case. And this is what we call the Dalton law. The total pressure is equal to the partial pressure of all components. But this is by the condition that all components have the same temperature. So here the temperature of component species A is the same as actually the temperature of B, same as the temperature of C, and so on. So all gases inside this container has the same temperature, and they occupy actually the same volume. So the total volume is equal to the volume occupied by gas A. It is the same actually the volume occupied by gas B, and so on. So all gases, every species actually occupies the whole volume. You know, gas expand actually to fill the whole space. So under this condition, we can say the summation of the partial pressure should equal to the total pressure. We call it the summation of all actually the partial pressure from I equal to 1 until actually all of the component, which is the number of component which is equal to n in this case. Okay. Like to calculate the properties of this gas mixture, we have actually we have two ways. Either we have the mass analysis or we have the volumetric analysis. But if I need to calculate, before I talk about gas analysis and volumetric analysis, if I need to calculate the total energy of this gas mixture, based on the modified actually Dalton law, which we call it actually Gibbs-Dalton law. Gibbs-Dalton law say actually the total property, like the internal energy, should equal to actually the internal energy of component A plus the internal energy of component B plus C plus so on, whatever the number of components. Like this, this is what we call the total internal energy, calculated in kilojoule. But usually in all property table, you will find the internal energy is given in the specific form. Any specific form, is the energy or any property per unit mass, calculated in kilojoule per kilogram. So usually you will find the internal energy in the table in the specific form. So the specific form is the total energy is equal to mass multiplied by the specific energy, specific internal energy. We call it U small in this case. This is the specific internal energy calculated in kilojoule per kilogram. If we multiply the specific internal energy by the mass, then we can get what we can get the total internal energy. We call it U capital. This is actually the total internal energy is equal to mass multiplied by the specific internal energy. This is we are talking here about what? We are talking here about the mixture. So the specific internal energy multiplied by the total mass for the mixture, that should equal to mass of component A multiplied by specific internal energy UA plus mass of component B multiplied by a specific internal energy of component B, and so on. Okay? Like this, we can calculate the enthalpy, the total enthalpy. Enthalpy is defined as what? Enthalpy is defined as what? The internal energy plus the flow energy, which is pressure multiplied by volume. So enthalpy does not have any physical meaning unless it is the summation of the internal energy, which is mainly function of the temperature of any gas, plus we call this term as the flow energy, because to have a flow we have to have a pressure in order to force the flow to go. So we call it the flow energy. Flow energy is pressure multiplied by multiplied by volume in this case. And like this, we can calculate the total enthalpy will equal to enthalpy of A plus enthalpy of B plus enthalpy of C, and so on. And we can express it also in the specific form. We can say mass multiplied by a specific enthalpy H small. This is the specific enthalpy calculated in kilojoule per kilogram. That should equal to mass A multiplied by specific enthalpy HA plus mass B multiplied by specific enthalpy HB, and so on. So to calculate any property for the mixture, it will equal to the summation actually of the properties for the all component in this case. One last important property is the entropy. We can say also mass multiplied by the specific entropy. That should equal to mass A multiplied by specific entropy SA plus mass B specific entropy SP plus so on. The entropy is a specific entropy is calculated in kilojoule per kilogram Kelvin. If you ask anybody what is the entropy, he will just tell you the entropy is a measure of randomness. If we have a gas inside a container, it will give us an indication about the randomness motion of the molecules. If you ask anybody, he will tell you entropy is a measure of randomness motion of the molecules. And if the temperature of the gas is high, that means actually it should have actually higher activity of the molecule. And in this case, the entropy should be higher in this case. Based on the third law of thermodynamics, the entropy is assigned the value of 0 when we have actually the absolute temperature is equal to 0 Kelvin. This is the third law of thermodynamics. Okay, so when the temperature increases, in this case, the entropy will be increased. And actually, the molecules will be more active in this case. And that's why we say entropy is a representation of actually the randomness motion of the molecule. But this is not totally correct. Entropy is energy. It is defined in kilojoule per kilogram Kelvin, the amount of energy absorbed by the molecules per kilogram of the gas for temperature rise 1 degree. Okay, so at the end it is energy. But this energy, cannot be converted to work. This energy absorbed by the molecules, we should be able to convert it to work. But this energy is not converted to work. Energy, which appear in the entropy term, cannot be converted to work. Why, Because if you look at the random motion of the molecules, you will find one molecule is moving in this direction, the other is moving in the opposite direction. So we don't have organized the form of energy so that we can take it and we can generate work. So this energy is a dissipated energy, dissipated in the kinetic motion of the molecules. That's why if you have a system and you want to calculate the losses within this system, you can calculate what's called actually the entropy generation. And I think actually the mechanical student know about this. From 203 and 204, you can calculate actually the entropy generation within the system. Entropy generation will give us about an idea about the losses within the system. Because as you know, if we have friction will be converted to what? Inside the system.
Heat. To heat.
Be converted to heat. But as the system, the gas is accepting heat. In this case, we can convert this heat into work. So we can utilize the heat losses due to friction. But can we do that?
No.
No, we cannot do that. Because actually this energy will be absorbed by the molecules. And it will be dissipated in the random motion of the molecules. And it will appear in the term of what we call actually the entropy in this case. Entropy will be raised in this case. If we have higher friction, the entropy will be raised. And if I need to calculate the losses within a system, I have to calculate the entropy generated within this system. So this is an idea about if we have a gas mixture. But in order to calculate the properties, we have two ways actually. We have to know about the concentration of the gases in this mixture. We have two ways. We have the mass concentration, mass basis, and we have the volumetric concentration. In order, either we can calculate the number of moles of a species, or we can actually calculate the mass of each species, and then we can know actually about the concentration of each species in a gas mixture existing inside a container. Okay, so first of all, let's consider the mass or gravimetric actually basis. So in the mass basis, if we have, let's say, a gas mixture, as we said, let's say we have gas component, gas A plus gas B plus gas C, and so on. They are mixed together. In this case, to calculate the total mass of this gas mixture, it will equal to the mass of gas A plus mass of gas B plus C, and so on, whatever the number of gases. Okay? So the mass will equal to the summation of all MIs, of all masses, of all species from I to equal to 1 until actually the number of species, which is N in this case. So mass will equal to summation of MI. And based on that, we can define actually the mass fraction. We call it Xi. Mass fraction of gas A should equal to the mass of this gas, Mi, divided by the total mass. So let's say we are talking about gas A. So in this case, Xa, the mass fraction of this gas, will equal to the mass, its mass divided by the total mass in this case. So this is the fraction out of 100%. That means actually the summation of all mass fraction from I to equal to 1 up to N, that should equal to what, Shabab? That should equal to 1. Because actually X1, let's say it is 0.2, X2 0.3, X3 actually is 0.4. So that means actually X4, if we have 4 gas components, should equal to 1 minus the summation of the other. As actually they have all actually to sum up to 100% or equal to 1. This is the mass basis. And I think you know about this. We have the volumetric, or what we call actually the mole basis. This is based on the volume of the system, the analysis of the volume, and the analysis of the number of moles instead of mass. And in this case, we count the number of moles. The total number of moles of the mixture will equal to number of moles of A, Na plus Nb plus Nc plus so on. So it will equal to summation of all actually number of moles actually of each component in this case. And based on that, we can define actually the mole fraction. Mole fraction will give it actually the Y. So Y will equal to the number of moles of each species divided by actually the total number of moles. And this gives us indication about actually the fraction of 100%. So the summation actually of all Yi, that should sum up actually to equal to 1. So the summation of the mass fraction should equal to 1 for all gases, and summation actually of mole fraction should also sum up to equal to 1 in this case. Is that clear, Shabab? Is it clear?
Yes, very clear.
I know this is something for you. It's a kind of just playing football. So let's say, but it's a good refreshment. We need it in this chapter. Okay. So if we have a mixture, how to calculate the molecular weight? We have the mass of any gas is equal to the number of moles multiplied by the molecular weight. You know the molecular weight is calculated in kilogram per kilomole. Kilogram per kilomole. The number of moles N is calculated in kilomole. And this is kilomole multiplied by kilogram per kilomole. So kilomole will go together. So this is the mass that should be calculated in kilogram. 1 mole for any gas, it's not equal to 1 atom. 1 mole actually equal to the Avogadro's number actually of atom for a given gas. So if we have a gas, the number of atoms equal to the Avogadro's number, we call it actually 1 mole of this gas. Okay. Usually, inshallah, we use the term kilomole. We'll be using here kilogram instead of gram, so that we can make it kilogram. So it will be molecular weight will be given even in the table. I have just uploaded for you some table. You will find the properties like the gas constant R and the molecular weight, specific heat for different gases. I have just uploaded for you some tables on the blackboard. This is actually part of the book on the internal combustion engine that I'm preparing right now. So you will find in this, you will find actually the molecular weight is just defined in kilogram per kilomole, and the number of moles is calculated in kilomole, and the mass is calculated in kilogram in this case. Okay. So if we have a gas mixture, That means actually the mass should equal to the summation of Ni multiplied by the molecular weight of each species. This is actually the mass in this case. And if we have a gas mixture, we can calculate the molecular weight of this gas mixture. Molecular weight will equal to mass divided by the number of moles. And mass is equal to the summation of Ni multiplied by the molecular weight for each component divided by the total number of moles. But here, شباب, Ni divided by total number of moles is the mole fraction Yi. That means the molecular weight of the gas mixture will equal to summation of the mole fraction multiplied by the molecular weight of each component. So this is شباب for the mixture. If we have a mixture, we need to calculate the molecular weight. So the molecular weight will equal to the summation of the mole fraction for each component multiplied by the molecular weight for each component. Okay? Right, this is the mole fraction. If we consider, we call it here شباب the average molecular weight or the apparent molecular weight. If we just flip it, 1 over the molecular weight will equal to N divided by mass. And N is equal to what, شباب? M divided will equal to M divided by the molecular weight, it will equal to summation of Mi divided by the molecular weight R. This is N equal to mass divided by the molecular weight. So the total N is the summation of molecular mass of each species divided by its molecular weight. This is divided by the mass. But we have Mi divided by total mass, we call it actually the mass fraction. So that should equal to the summation of Xi multiplied by the molecular weight R. And this, شباب, is 1 over the molecular weight. 1 over the molecular weight is equal to summation of Xi mass fraction multiplied by the molecular weight for each component. But the molecular weight itself is equal to summation of Yi multiplied by Mi. But what if I need, شباب, to calculate the gas mixture, the gas constant for a gas mixture? R, gas constant. R is divided by the universal gas constant, R bar, divided by the molecular weight. Okay? The universal gas constant, شباب, you know about 8.314 kilojoule per kilomole Kelvin. This value should be in mind. After 5 years or 4 years in engineering school, it should be actually, this value should be in mind. Okay? That should equal to universal gas constant divided by the molecular weight. But we have 1 over molecular weight is equal to what? Summation of Xi Mi. So that should equal to R bar divided by summation, 1 over the molecular weight. So this is R bar. 1 over the molecular weight will equal to summation of Xi multiplied by Mi. R is equal to R bar divided by the molecular weight. And 1 over the molecular weight is equal to summation of Xi multiplied by, no, is it summation of Xi divided by Mi, يا شباب, ها? Here, يا شباب. So this is Xi divided, please be focused, يا شباب. This is يعني Xi divided by the molecular weight Mi. Okay? So 1 over the molecular weight will equal to Xi divided by the molecular weight R. And this is multiplied by R bar. R bar divided by Mi, which should equal to R for this gas. That should equal to summation of Xi multiplied by the gas constant for each gas in this case. So again, يا شباب, here molecular weight is equal to summation of the mole fraction multiplied by the molecular weight for each component. If we consider 1 over the molecular weight, that should equal to the summation of Mi over total mass, which is Xi divided by Mi. So it is a summation of the mass fraction divided by the molecular weight of each component. The gas constant for the mixture will equal to R bar divided by the molecular weight. 1 over the molecular weight is equal to summation of Xi over Mi. But we have R bar divided by Mi, R bar over M, that should equal to the R or the gas constant for each component R. That means the gas mixture, يا شباب, should equal to the summation of the mass fraction multiplied by the gas constant for each component. Is that clear, يا شباب?
Yes.
So Do you have a question or something? So the guys from mechanical department, I think you know about this. This is from thermodynamics. You have good idea about this. Is it clear يا شباب؟ طيب. I will ask somebody to make sure that you are all following in. So, طيب, how we can convert the شباب from the mole fraction to the mass fraction? Let's say we have a gas mixture. Let's say here we have a gas mixture, and we have actually, let's say we have oxygen. So we have the mole fraction of oxygen, and let's say we have nitrogen, and the mole fraction of N2 is given, and the mole fraction, let's say, of argon is given, and so on, whatever the gases. The gases are expressed actually on the volumetric basis, or the mole fraction in this case. How we can convert from the mole fraction to the mass fraction? So we have the mole fraction for any component, xi is equal to the mass of this component divided by the total mass. And this mass of this component is equal to its number of moles multiplied by its molecular weight divided by the total mass. And the total mass is just a summation of the number of moles for each component multiplied by the molecular weight for each component. Okay? So if we divide here up and down by the total number of moles, here, total number of moles, so it will be Ni over N, which is equal to Yi, which is the mole fraction, multiplied by its molecular weight for this component, I, divided by summation of Ni over N, which is the summation of Yi multiplied by the molecular weight I. And this is how we can convert from the mole fraction, we can convert to actually mass fraction. If we have the mole fraction Yi for all gases, then in this case we can convert actually to the mass fraction. Like this example, let's say we have those three gases, O2, nitrogen, and argon. In this case, if I need to calculate the mass fraction of O2, so that should equal to its mole fraction, the mole fraction of O2, multiplied by the molecular weight of O2, which is 32, okay, divided by the summation of all gases. It will be the mole fraction of O2 multiplied by 32, plus the mole fraction of N2 multiplied by its molecular weight, which is 28, plus the mole fraction of argon multiplied by its molecular weight, which is almost 40. So in this case, if I calculate this, then I can calculate the mass fraction of the oxygen in this case. If I know actually the mole fraction of all gases, then in this case we can multiply by the molecular weight, and then we can convert it to calculate the mass fraction. Like this, we can calculate the mass fraction for nitrogen. It will be the same. But for the third gas, the last component, do I need to write down this equation again and calculate it?
No, just 1 minus the summation.
Exactly. So we have the summation of xi is equal to 1. If I calculated, we have three gases. I calculate xO2, xN2. That means actually the mass fraction of argon will equal to 1 minus the mass fraction of O2 plus mass fraction of N2. So usually, for the last species, I don't need to calculate, because actually the sum of all to 1, then in this case, X argon will equal to 1 minus those 1. Even also for those components, he may give you actually the mole fraction of YO2 and YN2. And they don't need actually to give you Y argon, because you need actually the mole fraction of argon, that should equal to 1 minus the mole fraction of O2 plus the mole fraction of N2. Okay? So usually the last species, we don't have actually data for it. Like this, we can just also get another equation to convert. This is to convert from mole fraction to mass fraction. We can do the reverse, convert from mass fraction to mole fraction, if those gases are actually given in the mass fraction. So Yi, you can just develop this equation, will equal to Xi divided by the molecular weight Mi divided by the summation of Xi divided by Mi. All of this is written in the slide, then we can convert. If I need to convert it from mole fraction to mass fraction, or from mass fraction to mole fraction in this case. Okay? طيب كلير يا شباب؟
Yes.
مشاري, is it clear?
Yes, دكتور.
Okay. طيب let's continue. If we have a gas mixture and we need to calculate the properties. Properties like يعني internal energy, enthalpy, entropy. But to calculate يا شباب the internal energy and the enthalpy, we need to know about the specific heat. Specific heat at constant volume, as you know. We have two specific heat at constant volume and the specific heat at constant temperature. And the specific heat يعني in general is the heat absorbed by the substance, the unit kilogram of this substance for temperature rise of 1 degree. Type, anyway, let's talk about the mixture properties. How to calculate actually the properties of a gas mixture. Let's say we have here again, we have a gas mixture of component A, B, C, plus so on, whatever the number of components in this case. But we can calculate the internal energy and the enthalpy, but in this case we know about the specific heat. We have the specific heat at CB, as you know, at constant pressure, which is defined as dH by dt when the pressure is constant. dH by dt at constant pressure. The specific heat at constant volume CV, which is the partial differentiation of the internal energy du by dt, but at constant volume. So what is the difference, شباب? Both of them are calculated in kilojoule per kilogram Kelvin. What is the difference, شباب, between both of them? They are the amount of heat added to, let's say we have 1 kilogram of a given substance, and we add heat actually. The symbol Q, ya شباب, we give it indication about heat. Okay, so you will find me just write it frequently. Q is indication about heat. So we added heat to 1 kilogram of a substance, and the temperature has been raised. Delta T is equal to 1. Either 1 Kelvin or 1 degree C, it doesn't matter. This is the temperature difference. So to raise, it is the amount of heat added per kilogram of a substance to have temperature rise 1 Kelvin. That means it is giving us indication about the energy storage capacity of a given substance. Okay, how much of energy this substance can absorb actually for a given temperature rise in this case. If this heat, ya شباب, is added under constant pressure, we call it actually, this is the specific heat at constant pressure. If heat is added under constant volume, we call it actually the specific heat at constant volume. But usually, شباب, if we have a substance in a container and you want to add heat, so what will happen to the gas, ya شباب, or the substance? It will what? It will expand. It will expand. So the only process or the only way, ya شباب, to have heat addition under constant pressure is through the movement of one of the boundaries. So this boundary here, if this is a piston cylinder device, this boundary should be moving in this case, because the gas will try to expand. If you want to keep the pressure constant, so you should allow actually for this expansion. You should leave the piston moving in order to keep the pressure constant. If this piston is closed, not moving, then in this case the pressure will be raised. In this case, the gas will try to expand, no movement, so the pressure will be raised. So in order to add heat at constant pressure, the boundary will be moving. And in this case, actually, in order to move the boundary, part of the input heat will be converted to work in order to move the boundary. And that's why at constant pressure you have to add more heat, because this heat will heat up the substance to have this temperature rise 1 degree C, and we have to add more heat in order to move the piston to keep the pressure constant. That's why you will find all the case CB is greater than CV. Because to have CB, we have to keep the pressure constant, we have to add more heat, so that the boundary should be moving in this case. So for any gas, you will find the specific heat at constant pressure is greater than a specific heat at constant volume. But what about the ideal gas? Ideal gas, ya شباب, we can treat any gas as an ideal gas under very low pressure, because the intermolecular forces in this case will be very low. So in this case, under very low pressure or very low density, we call it. In this case, we don't have any molecular order in this case. That's why all of the properties of the ideal gas can be only function of the temperature. That means we can just have the total differentiation here. Instead of partial differentiation, we can have the total differentiation. And in this case, we can say about what? We can say delta H, the total differentiation, equal to Cv multiplied by delta T. So we can remove this partial differentiation because under very low pressure, the ideal gas is depending mainly, or we can say only, on the temperature of the gas. So it will be equal to delta H will equal to Cv dt. Unlike this, delta U will equal to the specific heat at constant volume Cv dt. Okay? But if we have a gas mixture, so the enthalpy, the total enthalpy, will equal to the total mass multiplied by the specific enthalpy. This is for the mixture. It will equal to what, يا شباب? Mass A, let's say actually, okay, let's say mass A multiplied by enthalpy HA plus mass B multiplied by enthalpy HB plus whatever the number of components we can add here. Okay? Type enthalpy. Enthalpy, if it is ideal gas, H will equal to CVT. So it will equal to mass. H is Cv multiplied by temperature. And this is, let's say, شباب, instead of mass A, let's say mass 1. M1 Cv1 multiplied by temperature T1. But the temperature, شباب, for a gas mixture, T is the same as T1, is the same as T2. It is the same actually as the temperature for any species. So the temperature for species A or species number 1 is the same as the temperature for the mixture. We don't have variation in this case. So it will equal to M1 Cv1 multiplied by T plus M2 Cv2 multiplied by T plus the other component. If we divide here actually by temperature, so temperature can go together, and then let's divide by the total mass. So it will be mass divided by the total mass, this is 1, and this is M1 divided by the total mass, M2 divided by the total mass, and so on. M1 divided by the total mass, which is mass fraction x1, and this is actually the mass fraction x2. That means the specific heat for a mixture, Cv, is equal to what, شباب? Mass fraction x1 multiplied by Cv1, x2 multiplied by Cv2. Or we can say, شباب, the specific heat for a mixture at constant temperature will equal to just the summation of the mass fraction for each component multiplied by the specific heat for each component. For each gas, it should have a given specific heat at constant temperature and the specific heat at constant volume. And this is function of temperature. It is not constant value at any temperature. No, the specific heat is variable with temperature. Usually it has a parabolic, a kind of second order profile, Cv and Cv as function of temperature. Usually they have such a kind of profile. They increase with the temperature. That means, the specific heat to raise the temperature of water, let's say at 10 degrees C, to have 1 temperature degree C rise, it will be less than the amount of heat required to raise the same 1 degree C, but at higher temperature. Let's say at 100, 150. In this case, the specific heat will be higher. Let's get back. So the Cv of the mixture will equal to the summation of the mass fraction for each component multiplied by its specific heat. Cv for each component. Cv for the different gases, you will find it in the first table. I have just uploaded for you. For the different gases, you can get the specific heat for this gas. If you have a gas mixture, then you can sum up the mass fraction for each component multiplied by the specific heat to calculate the specific heat for the mixture Cv. Like this, Cv will equal to summation of xi multiplied by Cv. And as you know, شباب, the specific heat ratio K, it has a symbol also gamma. I know you may have some differences between the symbol and between the mechanical department and the chemical, and also in mechanical department even you will find some courses talk about the specific heat ratio as gamma and some name it as K. I will be going with K. So it is the ratio between Cv of the mixture divided by Cv of the mixture. But it is not equal to the summation of Cvi divided by Cvi. No. In order to calculate the specific heat ratio for a mixture, we have to calculate CB for the mixture, calculate CV for the mixture, then you can just divide them together, then we can calculate the key in this case. When do we have the relation between CB and CV? CB minus CV is equal to the gas constant R. And this is for the case of ideal gas. You know where this equation came from? I think you know. We have enthalpy is the internal energy plus flow energy. And for an ideal gas, we have pressure multiplied by specific volume equal to RT. You know about this equation, Shabab? PV equal to what? RT. Is it clear, Shabab?
Yes, the ideal gas law.
Yes. Then we can just remove PV and just replace it by RT. So the enthalpy will equal to the internal energy plus RT. Just differentiate, so delta H will equal to delta U plus R dt. Okay? And delta H is CB dt. Delta U is CV dt plus R dt. So dt will go with dt with this dt. So CB will equal to CV plus the gas constant R. Or we can say the difference between CB and CV will equal to the gas constant R in this case. If we just took this equation, combine it with this equation together, then we can just relate CV will equal to R divided by K minus 1, and CB will equal to K R divided by the same, K minus 1. So this يعني شباب based on the ideal gas relation. So for a given mixture, we can calculate CV for the mixture, we can calculate also CV, and we can calculate the specific heat ratio, which is CV divided by CV. Okay, Shabab? But it is not equal to the summation of CBI divided by CVI for each component. No, I have to calculate CB for the mixture divided by CV. The last, Shabab, is the partial pressure. We said the total pressure is equal to the summation of the partial pressure for each component. But the partial pressure itself is equal to what? Is equal to the number of moles for this component divided by the total number of moles multiplied by the total pressure. So the partial pressure for any component in a gas mixture is equal to the number of moles divided by the total number of moles, which we call it, Shabab, what? The mole fraction Yi multiplied by the total pressure. Then we can get, in this case, the partial pressure of component R. Okay? Is that clear, Shabab? Clear? Okay. I know this is a kind of, this is a kind of not more than refreshment for you, for all of you, but let's revise here. This is what I said. Started with the Dalton and Gibbs-Dalton law for partial pressure. Talk about this. Then we move. We said the condition volume should be the. This is the mole fraction. What we said, mass fraction and the mole fraction. How to calculate the mass fraction and the mole fraction, and the molecular weight of the mixture, and 1 over the molecular weight, based on which, based on that, Shabab, we can calculate. Also, if we can convert from the mole fraction, this is the relation. From mole fraction, we can convert to mass fraction, and here is the reverse, from mass fraction to mole fraction. As a gas constant R, we equal to R bar over M, and it will equal to summation of mass fraction multiplied by the gas constant for each component. If we have a Shabab compound, like diatomic compound like carbon dioxide, to calculate the molecular weight, it is equal to the molecular weight for each component multiplied by the number of moles. So carbon, its molecular weight is 12, and O2, O is 16 multiplied by 2, it will be 32. So 32 for O2 plus 12, it will be 44. And this is the molecular weight for carbon dioxide. This is something I should not mention. You should, we are already aware about that. This is CB of the mixture, as we have learned, and this is CV. To calculate the gas, the specific heat ratio is CB divided by CV. And this is Shabab, the partial pressure, which is the summation. The total pressure is the summation of the partial pressure of all components, and the partial pressure is equal to is equal to number of moles divided by, for this component, divided by the total number of moles, and that should equal to يا شباب. So that should equal to the mole fraction. The mole fraction, we call this one as Yi. Okay, the mole fraction multiplied by the total pressure. Is that clear يا شباب? Clear? So the partial pressure for each component is equal to the mole fraction of this component in a gas mixture multiplied by the total pressure. Here يعني is an example. Those يا شباب are all يعني just indicative example يعني they are very very simple actually at your level, but let's يعني go with it. It is important يا شباب to practice this. I will need this later on. Okay. طيب here is an example. Let's look at this example and see how we can proceed with it. So in this example, شباب, we said we have air. We assume air as only oxygen plus nitrogen. And this will be the assumption شباب, throughout this course. Throughout this course, while writing the combustion equation for any fuel, I will be consider the combustion with air, and I will assume actually air as only 21% by volume O2 plus 79% N2. That will be the assumption that we will go with throughout actually this course. Okay. Right, let's look here. He said in this example, air is defined, as I told you, air is almost approximated to 21% O2 plus 79% N2. And this is based on the mole basis, molar or volumetric basis. Okay? So this air, if we have actually one molecule, if we divide it by 21, this is 21% O2 divided by 21 here, both sides. So each one molecule of O2 will have 79 divided by 21, which is 3.76 N2. So each one molecule of oxygen in the air should have actually 3.76 N2 molecules. 3.76 molecules actually of nitrogen in this case. Okay. He said, let's assume we have a gas mixture that actually consists of 1 mole of O2 plus 3.76 mole of N2. Okay. Right, we have the molecular weight of O2 is equal to what? Molecular weight of O2. You should keep this in mind. It's 32, and the molecular weight of N2 is 28. Right. The total number of moles. Total number of moles will equal to the summation of number of moles for each component will equal to 1 plus 3.76. So it will equal to 4.76. So if I calculate the mole fraction of O2, that will equal to the number of moles of O2 divided by the total number of moles. Number of moles of O2 is 1 divided by the total number, which is 4.76. If you calculate this, the mole fraction should give you a value of about 0.21, which is the volumetric concentration of O2 in it. Like this, Yn2 is equal to a number of moles of N2 divided by total number of moles, which is 3.76 divided by 4.76. It will be equal to almost about 97. This is the percentage of N2. Okay. And you don't need actually to calculate Yn2 because we have two components. So Yn2 is equal to 1 minus YO2. Okay, because the summation of both of them should equal to 1. Anyway, this is really something very simple. But this is the mole fraction. Can we calculate the mass fraction? In this case, we need to calculate the mass fraction is the mass for each component divided by the total mass. And the mass is equal to number of moles multiplied by the molecular weight. Okay. So let's say the mass fraction of O2. That should equal to actually the mass of O2 divided by the total mass. Type the mass of O2 is equal to what is your number of moles of O2 multiplied by the molecular weight of O2. Number of moles is 1 multiplied by 32. That should be the mass of O2 in kilogram. Like this, the mass of N2 is equal to its number of mole of N2 multiplied by its molecular weight. Number of moles is given 3.76 multiplied by 28. You can calculate this number will be in kilogram as well. And the total mass is the summation of all masses, summation of MI, which is mass of O2 plus mass of N2. You can calculate this term as well in kilogram. Then we can calculate mass fraction of O2 will equal to the mass of O2 divided by the total mass. And we have the mass fraction of N2 is the same, but as both of them sum to 1, so it will be 1 minus the mass fraction of O2. Now what about the molecular weight of the mixture? Molecular weight of the mixture is equal to summation of Yi multiplied by the molecular weight for each component. So that means it is equal to the mole fraction of O2 multiplied by the molecular weight of O2, which is 32, plus the mole fraction of N2 multiplied by its molecular weight, which is 28. Mole fraction of O2, which we have calculated, 0.21. Mole fraction of N2 we have calculated 0.79. Then we can, in this case, calculate the mole fraction, the molecular weight, actually, the molecular weight of the constant. And the gas constant for the mixture equal to the universal gas constant, R bar or R universal, divided by the molecular weight. We have calculated this is the molecular weight, and R bar, you have to keep this in mind. This is actually 8.314 kilojoule. This is kilojoule per kilomole Kelvin. This is R, this is the universal gas constant because we divide by the molecular weight. But the gas constant for each component is kilojoule per kilogram Kelvin. So this is the universal gas constant, R bar per kilomole. Okay, kilojoule per kilomole. The gas constant is kilojoule per kilogram. And the gas constant is equal to the universal gas constant divided by the molecular weight. Okay, Shabab? Is it clear? I know, Yani, this is something is just a revision, but I just went through it, Yani, in details. You can even, this is Yani, some level here that if you can, this is another example very similar, but the masses are given here instead of number of moles. You can even, if you want to, you can make this table. If you want to have يعني organized solution. يعني later on, شباب, inshallah, when we start next class writing down the combustion equation, you will see you may need actually to have a kind of table just to make actually the calculation يعني organized and simplified. Here the masses for each component is given. Then we can sum them up, calculate the total mass. Molecular weight for each component, we can write it down. Then we can calculate the mass fraction, the mass for each component divided by the total mass, can calculate the mass fraction. Then we can calculate the number of moles for each component will equal to its mass divided by the molecular weight. Here actually the mass for each component divided by the molecular weight, we can get the number of moles for each component. Then we sum them up, get the total number of moles. Then in this case we can calculate the mole fraction as well, will equal to the number of moles for each component divided by the total number of moles. And they should sum up actually to 1. The molecular weight is the summation of the mole fraction multiplied by the molecular weight for each component. You can calculate the mole fraction multiplied by the molecular weight for each component. And then you can just calculate this for all species, sum them up, that will give us indication about the molecular weight. And the gas constant is the universal gas constant divided by the molecular weight. This is also Shabab, another example. You can just practice it. It is the same way. Okay. So Shabab, here you can use this table, and then you can just calculate the number of mole and calculate yi this case, this way. But there is another way. If we have the mass fraction, can we get the mole fraction directly through the calculation here? This is what I did here. So I have given here, but in this problem he gives the mole fraction. Then in this case I just used this equation, mass fraction as function of the mole fraction. If the mole fraction is given, just I can apply this equation directly in order to calculate the mass fraction. Otherwise you can just list this table and just stay with it. But this may take some time. If not, if you don't need the table, don't do it. You can just apply the equation directly. This equation can convert directly from the mole fraction to the mass fraction.